From today in solid state physics, we are going to start a new chapter, magnetism. Actually, this magnetism is a very important chapter of solid state physics, and it is important for various types of students and researchers too. In fact, almost all universities syllabus in India and abroad of solid state physics contains this chapter from B.Sc level to M.Sc level, and it is equally important for the engineering students of material science. And at present, material science is actually a vital field of research. There are so many workers working in the field of material science, particularly in nanotechnology. And whenever you study the nanomaterials, one of the important properties which we discuss is magnetic properties. So magnetism is a very important chapter, and it will prove its importance to the students from my videos. Okay. In fact, whenever you talk about magnetism, one thing you must think about this magnetism, that this magnetism arises from the motion of the electric charges, okay, and also by the internal or intrinsic magnetic moments of particles like electrons. In fact, electrons have actually different type of motions. When you talk about the spin of electron, then with a spin of electron, magnetic moment is associated. When you talk about the orbital angular momentum or orbital motion of the electron about the nucleus, then with that angular momentum, the magnetic moment is associated. Okay, and apart from that, whenever due to the interaction with a magnetic field there is a change in orbital angular momentum, that also causes the dipole moment. So actually this magnetism is strictly related to quantum mechanics. This is a phenomenon exhibited by the quantum system. Okay, so you can say that magnetism is inseparable from quantum mechanics, because when you talk about a strictly a classical system in thermal equilibrium, and if you place a classical system in thermal equilibrium even in an external magnetic field, it will be not magnetized, it will not display any magnetic moment. So magnetism is actually a quantum mechanical phenomenon, not a classical phenomenon. Again, I am repeating this fact that if we talk about a strictly classical system in thermal equilibrium, such a system cannot display magnetic moment even when we place the specimen in a magnetic field. Okay, because so actually when you talk about magnetism, you must think on the atomic level, on the microparticle level. Only then you can understand the idea of magnetism. Okay, and as I have told you that this magnetic moment of a free atom is caused by three reasons, or there are three sources you can say for the magnetic moment of a free atom, and that are a spin of electron, which we denote by symbol vector s, which represents the spin angular momentum, and the orbital angular momentum of electron, that is represented by L, and change in this L due to the interaction with magnetic field. Okay, so definitely when we will study the concept of this chapter, always we will think about the classical, about the quantum system, and our explanation will be on the basis of quantum mechanics, because any type of magnetism can be explained in a correct manner only by the quantum mechanical approach. Okay. In fact, there are four fundamental forces, and one of them is the electromagnetic forces, in which magnetic force actually exists. So this is actually a fundamental force in nature, and this plays a very important role, a key role in various physical phenomena and technological applications. Okay. Actually, the magnetic materials are vital in industries ranging from electronics and communication to medicine and energy storage. Okay. So actually understanding their properties is key to their effective application. So if you want to know the application of these magnetic materials in various fields of science and technology, definitely first of all we have to understand the physics behind those applications. And when you talk about the physics behind those applications, that means we have to study the different properties of the magnetic materials. So actually, when you talk about magnetism, our prime aim in this chapter will be what? That will be the detailed study of different type of magnetic materials. We will see later on there are actually basically six types of magnetic materials, and in our a series of videos we will see the discussion on all the six types of magnetic materials in very detail. So this is a long chapter, and there will be a large number of videos provided by me on this subject. Okay. But whenever you talk about the study of magnetic materials and its different properties, there are some parameters in terms of which we actually discuss any magnetic material. So first of all, in this introductory lecture, I will introduce you the basic definition of those parameters. That will be just an introductory fact. Okay. So what are the important terms of definition, or what are the important parameters which will be actually used to discuss the different type of magnetic materials? First of all, we will learn about those in this introductory lecture. Then after this introductory lecture, we will uh, study the different type of magnetism separately, or different type of magnetic materials separately. So let us see. The first parameter for the study of magnetic materials is intensity of magnetizing field, which is denoted by the symbol H. Okay. Sometimes people does not say intensity of magnetizing field, they generally simply say magnetizing field H. But when you will use the term intensity, that will be more appropriate. In fact, let us consider that this is a magnetic material. Magnetic material means a material which can be magnetized, in which the property of magnetism can be induced. And for magnetizing this material, we have to place this material into an external magnetic field. And that external magnetic field is denoted by the symbol BO, O for outside. This is the outside field or the external field which will actually magnetize this material. Okay. It will induce magnetism in this material. So BO is called external magnetizing field. Okay. And this is your material which has been placed in this external magnetic field. Okay. So any external magnetic field in which we place the magnetic material to magnetize it, that is called actually the magnetizing field. So this BO is what? This is magnetizing field. Okay. Now when you say intensity of magnetizing field, how it will be defined? Actually, the intensity of magnetizing field is defined as the ratio of the magnetizing field and the permeability of free space. So if you denote the intensity of magnetizing field by the symbol H, H is defined as BO divided by mu naught. Okay. Or you can say that BO is equal to mu naught times H. Okay. So I have written here, you can see in a magnetizing field, the ratio of magnetizing field BO to the permeability of free space mu naught. And what's the value of mu naught? I think you can remember it. This is 4 pi into 10 to the power minus 7 Tesla meter per ampere. This is the value of mu naught, which is a universal constant, and this is called permeability of free space or permeability of vacuum. Okay. So basically, this intensity of magnetization H is defined in this manner. When you will divide the magnetizing field BO by this mu naught, then you will get the intensity of magnetizing field. Okay. Or you can say that this BO is equal to mu naught times H. Now you can see, since the magnetizing field BO is a vector and mu naught is a scalar, okay, so when you will divide a vector by a scalar, result will be a vector. So this intensity of magnetizing field H is a vector. Okay. And since this mu naught is a positive quantity, its value is positive. And you know, when any vector is multiplied or divided by a positive number or positive scalar, the resulting vector has a direction as the original vector. So here definitely this H will be in the direction of BO. So intensity of magnetizing field H is directed in the direction of the external magnetizing field BO. Okay. And its SI unit, you should remember it, this is ampere meter inverse. SI unit of magnetizing field is what? This is ampere meter inverse. Okay. So in this material, when this material will be placed in this outside magnetic field, it will get magnetized, and this H will be directed in the direction of BO. Okay. Now the second important parameter to discuss the magnetic material is intensity of magnetization, or simply we say it magnetization. There is no need to say intensity of magnetization. You can call it only magnetization, and generally people denote it by the symbol capital M. It is also a vector, you can see. Now how this intensity of magnetization or simply magnetization M is defined? Actually, when you place a material or a specimen of magnetic material in a magnetizing field, okay, then in fact magnetic dipole moment is developed in this material. Okay. In this material, magnetic moment will be developed. Okay. And that is also called induced magnetic dipole moment. Okay. The material which was unmagnetized, now it is magnetized and magnetic dipole moment is developed. Okay. This magnetization is defined as the induced dipole moment per unit volume. Induced dipole moment per unit volume. So if you consider that V is the volume of this specimen, and when it is magnetized, then the dipole moment developed in this specimen is m, small m. So in volume V, the induced dipole moment developed is m. So in unit volume, the developed induced dipole moment will be m divided by V. And in accordance with that definition, the induced dipole moment per unit volume is called magnetization. So m is defined as a small m divided by V. Okay, very simple. Where this small m is induced dipole moment of the specimen, and V is the volume of the specimen. Okay. Now, the SI unit of this magnetization is also ampere meter inverse. That is the unit of magnetization and unit of intensity of magnetizing field. Both are same, ampere meter inverse. And again you can see, since this dipole moment small m is a vector, and so the magnetization capital M is also a vector. Okay. Now, actually, this magnetization vector is directed in which direction? Actually, when you place the specimen or the magnetic material in an magnetizing field, then the induced dipole moment, that is M, you can see from here that this capital M will be always parallel to a small m. That is, magnetization is always in the direction of induced dipole moment. Okay. But the induced dipole moment developed in this specimen may be in the direction of a magnetizing field BO, or it may be in its opposite direction. Both is possible. It depends on the nature of the material. Okay. Actually, when this M is parallel to BO or parallel to H, then it is called positive magnetization. Okay. But when M is anti-parallel to BO or H, then it is called negative magnetization. We will see later on, in case of diamagnetic material, negative magnetization exists. When a diamagnetic material is placed in an external magnetic field, the magnetization is developed in the opposite direction of the magnetizing field. But when you will place a paramagnetic material or a ferromagnetic material in an external magnetic field or magnetizing field, then you will see that magnetization is developed in the direction of the magnetizing field. Okay. So there are two possibilities. Okay. As you can see in this figure, I have shown here that the magnetizing field BO or H is directed from left to right, and this is our specimen, you can see. Now, in this first figure, you can see the dipole moment is directed from left to right, and in the direction of dipole moment, always this magnetization lies. So this capital M is in the direction of a small m, and a small m is in the direction of H. So this is the case of positive magnetization. Okay. But in this second figure, you can see that here the dipole moment developed is from right to left. Okay, right to left. And so this magnetization will be also from right to left. But the magnetizing field is from left to right. So this is the situation of negative magnetization. Here actually I have written S and N, that represents actually the south pole and north pole. Actually, conventionally we suppose that dipole moment is directed from south pole to north pole. As in case of electric dipole, The dipole moment is directed from negative charge to positive charge. So a south pole of a magnet is just equivalent to a negative charge and north pole is equivalent to a positive charge. Okay. So magnetization can be in the direction of magnetizing field and it may be in opposite direction of the magnetizing field. When magnetization is in the direction of magnetizing field, then it is called positive magnetization. Okay. And if it is in the opposite direction of magnetizing field, then it is called negative magnetization. And this negative magnetization is the situation which is found in case of diamagnetic material. We will learn it later on. Okay. So magnetization is our second parameter to discuss the behavior of magnetic material in a magnetic field. Now we will see the third important, most important parameter, which is called magnetic susceptibility, and this is denoted by the symbol chi. Actually, this magnetic susceptibility is defined in this manner. It is defined as the ratio of the magnitude of magnetization M and the magnetizing field H. You can see this capital M is what? In this formula, this capital M represents the magnitude of the magnetization. Okay. And capital H, this is the magnitude of the intensity of magnetizing field. So when you divide this M by H, then you get chi. In other words, it is also said that M is actually proportional to H. And when you will replace this proportionality sign from here, this is chi times H. Okay. And so chi is equal to M over H. But in the basic definition, you can say that the ratio of magnitude of magnetization to that of the magnetizing field is called magnetic susceptibility. Okay. Now you have learnt that magnetization M has the unit ampere meter inverse. You have learnt. And H has also unit ampere meter inverse. Okay. So M over H, the unit ampere meter inverse in numerator and denominator will cancel out, and so you can say that this chi has no dimension, no unit. So it is a unitless and dimensionless number. Okay. But what is its physical significance? Physically, what fact is actually indicated physically by this magnetic susceptibility? In fact, physically, this magnetic susceptibility represents the ease with which a magnetic material can be magnetized. It means how easily a magnetic material gets magnetized when it is placed in a magnetic field. That is measured by this property. If you can say that this chi has a large value, what does it mean? Chi is large, that means such a material can be easily magnetized. Okay, can be easily magnetized. But if chi is small, such a material cannot be easily magnetized, but for magnetizing such a material, you have to apply a very strong magnetic field. Only then such a material can be magnetized. And as you have seen that this magnetization M may be in the direction of H or may be in opposite direction of H. Yeah, as you can see in this figure. In first figure, M is in the direction of H, but in this second figure, M is in opposite direction of H. So this chi may be positive or it may be negative. Both. Chi will be positive when there is positive magnetization. It means magnetization is in the direction of the magnetizing field. But this chi will be negative when the magnetization has taken place in opposite direction of the magnetizing field, or you can say that this magnetization is negative. So chi may be positive or chi may be negative. As I have told you earlier that in case of diamagnetic material, there is negative magnetization. That is, diamagnetic material gets magnetized just in opposite direction of the magnetizing field. So the value of this chi will be negative for diamagnetic material. But if you will talk about the paramagnetic material, you will see later on that a paramagnetic material has positive magnetization, and so this chi will have a positive value for a paramagnetic material. All these things we will discuss later on. Okay. So magnetic susceptibility is actually the most important parameter whenever we will discuss the behavior of any magnetic material in a magnetic field. Definitely we will calculate the value of this magnetic susceptibility, and the value of magnetic susceptibility decides the behavior, decides the nature of the magnetic material. So it is the most important parameter, and you should remember this definition. Okay. Now finally we are going to see also a very important parameter which is called magnetic permeability. Okay. What is this magnetic permeability? What are its important characteristics? We will learn now. Actually, see, when you place a magnetic material or a specimen of magnetic material in a magnetizing field to magnetize it, then this mu, which is called magnetic permeability, that is defined as B over H. What is this B here? Actually, when you place a specimen in a magnetizing field, let us say BO, this is magnetizing field or outside field. Actually, then magnetization is developed in this specimen, and due to that, an internal magnetic field is also developed inside it. Okay, which is denoted by the symbol Bi. So if you consider a point P inside the specimen, then net magnetic field at a point inside this material will be not equal to BO, but the total magnetic field inside the material will be B, which is equal to BO plus Bi. Here Bi is the internal magnetic field, or it is also called induced magnetic field. Okay. So magnetic field inside the magnetic material is not same as the outside field or as the applied field or the magnetizing field. Okay. We will see about this. This is called total magnetic field inside a magnetic material. We will see later on about this B. So when you divide this total magnetic field inside a magnetic material by the intensity of magnetization, okay, intensity of magnetization H, then you get a quantity which is actually denoted by the symbol mu, and it is called the magnetic permeability. So basically this magnetic permeability mu is defined as B over H, okay, where B is the magnitude of the total magnetic field inside the material. Okay. So I have written here, you can see, when a magnetic material is placed in a magnetizing field, the ratio of the magnitude of the total magnetic field inside the material to that of intensity of magnetizing field is called magnetic permeability. And so mu is equal to B over H, or B is equal to mu H. Okay, B equal to mu H. In fact, what is the physical meaning or physical significance of this mu? In fact, this mu is a measure of degree to which a magnetic material can be penetrated or permitted by the magnetizing field. It means how much a magnetic material is penetrated by the magnetic field, that is actually measured in terms of mu. If mu is larger, it means the material is more permeable to the magnetic field. Magnetic field will penetrate into the material to a larger depth if mu is larger. But if mu is smaller, then penetration of magnetic field inside the material will be very little. That will be a smaller. Okay. Now you can see that since mu is a ratio of magnitude of B and magnitude of H, so this is a scalar quantity. So it is a scalar, not a vector, and its HI unit is Henry meter inverse. Here H stands for Henry. This is Henry meter inverse. Okay. Now just related to this mu, we also define a very important parameter which is called relative permeability, and it is denoted by the symbol mu r. In fact, when you talk about relative permeability, that means permeability of a material with respect to the vacuum. That is, how many times permeability of a material is greater than permeability of vacuum. That is called actually relative permeability. So if you want to find this relative permeability, or then you have to divide the permeability of the material by the absolute permeability of free space. Okay. In other words, it is also defined like this. This is defined as B over B naught. This is the basic definition actually, where B is the magnitude of total magnetic field inside the material, and BO, this is magnetizing field or outside field. And you have seen that when the material is placed in a magnetic field BO, then a magnetic field is also internally produced inside this material, which is denoted by the symbol Bi. So at any internal point, the total magnetic field is the vector sum of BO and Bi, and that is actually denoted by B. So when you will divide this B by the magnetizing field BO, then you get a number which is denoted by the symbol mu r, and that is called relative permeability. But as BO is equal to mu naught times H, just like that this B is equal to mu times H. And so this H and H will cancel out, and this is simply mu over mu naught. So basically we say that this mu r is the ratio of permeability of the material and that of the free space. Okay. So this just measures how many times the permeability of a material is greater than the permeability of free space. Since mu r is a ratio of two similar quantities, mu and mu naught, and mu naught both will have this dimension Henry meter inverse, so definitely this mu r will be mere a number. It will be a dimensionless and unitless number. Okay. It will have no dimension, no unit. Okay. So this is mu r. So these are actually the four parameters which will be needed in our discussion of different type of magnetic materials. So before starting the proper chapter of magnetism, proper study of different type of magnetism, I have introduced you with these parameters. Okay, because these terms of definitions will be invariably used in our discussion. Okay. Now we are going to see a very important relation, and this is relation between the permeability and susceptibility. how permeability mu is related to the susceptibility chi. Now let us see. And for this you have to consider a magnetic material or a specimen of a magnetic material placed in an external magnetic field BO. And I have told you several times that when the material gets magnetized, an induced magnetic field is developed inside the material. So at any internal point, the total magnetic field or the resultant magnetic field is equal to the vector sum of the outside magnetizing field and the internal field or induced field. This subscript I stands for induced field or internal field. Okay. One thing you should remember here, that this Bi may be in the direction of BO, and Bi is in the direction of BO when M is positive, when magnetization is positive. In case of positive magnetization, the induced magnetic field developed inside the material is in the same direction as that of the direction of outside magnetizing field. But this Bi is just in the opposite direction of the magnetizing field. Okay? And this will happen when magnetization M is negative. It means if you talk about diamagnetic material, then Bi will be in opposite direction of B. And so at an internal point, the resultant magnetic field will have a lesser magnitude than BO. But in case of paramagnetic material, ferromagnetic material, the Bi and BO are in same direction. So magnitude of the resultant magnetic field at an internal point will be greater than this applied magnetic field. Okay. But here I have not considered the negative sign, but that may be possible. How we can account for this negative sign, we will see later on. Now, BO, you have learnt that this BO is equal to mu naught H. But what's the reason of production of this Bi? Why Bi is produced? This is due to this M. So actually Bi is proportional to M. And so Bi is given as mu naught times M. Okay. BO is given as mu naught times H. You have already seen in the very beginning of here. This BO is equal to mu naught times H. Okay. And similarly, since Bi, internal or induced magnetic field, is produced due to the magnetization, so Bi is given as mu naught times M. You have seen that H and M both have same dimension, same unit. Okay. So what will be this BO? When you will substitute these two value here, then B will be equal to mu naught times H plus M. Now, as I have told you that this M may be in the direction of BO or may be in opposite direction of BO, and H and BO are always in the same direction. So you can say that this M may be in the direction of H or may be in opposite direction of H. In case of negative magnetization, actually H will be opposite to M. Now, we consider that what will be the resultant then? If H is either parallel to M, then resultant will be H plus M, because when two vectors are parallel, the magnitude of resultant is simply the sum of their magnitudes. And if they are in opposite direction, then the resultant will be H minus M. Okay, resultant will be H minus. But I will write only H plus M. And whenever needed, we will say that M is negative and then we will put the minus sign. So let us take H as a common factor. But you can't divide a vector by another vector because the division operation is not defined in case of a vector. So I am now talking about the magnitude of this B, okay, and also the magnitude of this H plus M, which will be simply H plus M or H minus M, but as I have told you, I will write only H plus M, and when needed, then we will put the minus sign. So when you will take H outside and divide by that H to the term in LHS, your result will be B by H equal to mu naught times 1 plus M by H. Okay, but you have seen that this B by H, this is equal to what? This is equal to mu. B over H is equal to mu. B over H is equal to mu. Okay, and here is mu naught, and you have also learned that M over H is equal to chi. This is magnetic susceptibility. Okay, and mu over mu naught, this is equal to mu r. So when you will divide this mu by this mu naught, your result will be mu r, and mu r is equal to 1 plus chi. Okay, so you can see that actually this mu r is related to this chi by this relation. Okay, the difference between the value of mu r and chi is equal to 1. Now, as I have told you that in case of positive magnetization, chi is positive. Chi is positive. And then mu r will be equal to 1 plus chi, and this will be greater than 1. It means in case of such a material, the relative permeability will be greater than 1. Okay, but in case of material whose magnetic susceptibility is negative, then actually mu r will be equal to 1 minus chi. Minus sign has been substituted here for the negative value of chi, and for those materials mu r will be less than 1. Okay, as it can be seen in case of diamagnetic material. Okay, so mu r is in general greater than 1. Okay, but for materials whose chi is negative, that is whose magnetization is negative, in case of which the induced magnetic field developed inside the magnetic material is in opposite direction of the magnetizing field, in such cases mu r is less than 1. Okay, so this is the relation between the, the permeability and the magnetic susceptibility in SI unit. But if your aim is to write down this relation in CGS system, then this relation which I have written here, this relation is then written like this: B equal to H plus 4 pi m in CGS unit. And this relation which I have mentioned in this equation 7, that is written as mu equal to 1 plus 4 pi chi in CGS unit. But we will adopt this relation written in SI unit in our further calculation. Okay. Actually, as I have told you, the prime aim of this chapter is to discuss the different type of magnetism or different type of magnetic materials. Okay, and these magnetic materials are classified on their response to an external magnetic field and the alignment of their atomic magnetic moments in accordance with the applied field. So on the basis of the values of these parameters, these parameters, particularly the value of chi, particularly the value of m, these values of m, values of chi, these decide the nature of the magnetic material. And on this basis, it is found that there are basically 6 types of magnetic materials, okay, which are actually diamagnetic materials, and the magnetism exhibited by diamagnetic materials are called diamagnetism. Then second one is paramagnetic materials, and its properties is called paramagnetism. Third one is ferromagnetic materials, and it exhibits ferromagnetism. Fourth one is anti-ferromagnetic materials, and they exhibit anti-ferromagnetism. Okay. Fifth one is ferrimagnetic materials, and they exhibit ferrimagnetism. And finally, the sixth one is superparamagnetic materials, which exhibit superparamagnetism. So, these 6 types of magnetism we will discuss in very detail in our forthcoming videos. So, this was just a brief introduction regarding this chapter, and from the next video we will start our concept in accordance with the syllabus of different uh, university examination and competitive examination. Okay, so thank you very much.